Okay, I think we are ready. Let's wait 2-3 minutes more. You could use whatever you want. However, the TA will get two totally different files. He will grade based on those files, right? But you don't have access to them, just to check the correctness. But feel free to use real data. Feel free to use the dummy files that we shared with you. It's up to you. You can make your own. Doesn't matter, really. As long as you can handle any file, it should be fine. Okay. So make sure you don't have any restriction on read length, on the structure of the file. If you have extra line between those every 4 lines, you should handle them well. So be careful to these little things. Because this is real life. This is how you deal with real files. Okay. If there's lowercase as well, you should handle that. There's lowercase, uppercase, especially in the genomic data, the genomic sequence itself. Okay. It's okay to have lowercase in the ID, the identifier. It's okay to have it in the quality, base quality. That's fine. Okay. So we will probably extend the assignment for 2 days more. Okay. So you ask until Wednesday, right? Okay. So let's have it on by the end of Wednesday, Atlanta time. Okay. So I don't know if the winter is always this way in Georgia. 1 week is hot, 1 week is cold, but still nice, much nicer than what we have in Europe. Snowing for 6 months or so. At least you'll get some sun every once in a while. All right, so maybe we can start. Okay, so good morning, everyone. For today, we will have a different topic. We'll start dealing with those genomic sequences. So we've been talking about sequencing. We've been talking about how we get the genomic data, either by simulation and some other ways. We will see it right now. So I would like to remind you, all the lectures are recorded on YouTube. If you missed something, please watch it on your own. However, there is a delay of 1 week between the actual lecture and the recording. So pay attention to that. We discussed last time 3 ways to obtain genomic data. So the first one was generating the real data, and this is the most expensive way. So you have to pay for the machine, for the technician, for the reagent, for the chemical molecules to get the sequencing yourself. Or you could go the easiest way, just download any data you are looking for. And we already see different ways of where we can download this data. There are multiple databases that you can access publicly and for free. If you are interested in human, in other species, still you can access them. The third way we were talking about is simulating those data. If you'd like to control something, mimic the actual hardware, the instrument itself, how it generates those data, so you could do that, right? You could plug in the error model that you are interested in, and then sequence those read based on that model. So this method, it's very nice if you're interested in the properties of those machines. Imagine that there is a new instrument coming next year, and you'd like to study that. So you could simulate and then compare whatever you get from the simulator with the real data that you are getting from the instrument. So you can understand what is happening and see if there is something you could fix. And normally, if you are able to design a simulator, then you are able to build an error correction method to correct the error in those read coming from the machine. Because you already understand what kind of error, what kind of distribution for those error. Is it stochastic? Is it always random along the sequence? Or as in Illumina, we always have those error toward the end. The last 30 character of the read, normally errorness. If you know this in advance, so you could build your own error correction method to just trim the last piece of data, okay? Or you could just ignore them when you do any further analysis. For example, you would like to do alignment, you would like to do indexing, you would like to do anything as a computation as part of the analysis. So you could just ignore that last part of the read sequence. Now we discuss two important formats. Those, whenever you deal with bioinformatics topic, you will deal with FASTA and FASTQ format. And we discuss what is inside. This is the FASTQ. And we will see another example of how you deal with it. I already assigned this exercise. There's no grade, there's no point, no credit for this exercise, just something to play with, okay? And I ask you to solve it, and there are actually two ways of solving it. So if you already solve it, I'm going now to include the answer in the today lecture, so you can check it out in iCollege and see if your answer is correct. And we said why there are two ways to solve it. If you consider this piece of data, 4 C's, now the markers are gone. Do we have them? No. Okay. They were empty anyway. So if you consider those 4 C's, you could, if I ask you to count how many 2 C's we have, so you could count the first 2, and then the things in the middle, and then the last 2, right? This is one way of doing it. Otherwise, you could just consider the first 2 and the last 2, and that's it. And both of them are correct. It depends on how you would like to implement this algorithm. You would like to have all overlapping pieces or just non-overlapping pieces, okay? This is the second solution. You could check it out and see which one. Oh, thank you so much. I appreciate it. Is it working? Oh, nice. Let's have the eraser. Should get +1 for that, right? Yeah, please write down your name. All right. And we discuss, we have 3 types of ways to solve this puzzle. We could have one straightforward way of solving it. The other way is very difficult. And the last one is kind of impossible. It's really challenging. It's really difficult. And the first way was when you have the picture in front of you and you'd like to solve that puzzle. So you bring every single piece from the puzzle and you'd like to compare with different location in that picture and see, does it exist here or there, and so on. And after doing that, you could solve the puzzle. However, you could make some errors, right? Especially in area where it's hard to recognize. For example, this area, all of them looks exactly the same thing, right? How you would be 100% sure that the piece located here was not originated from here, right? So you could make some errors, and those errors coming from the sequencing machine, okay? So the exact same story, we have it in real life. And this is what we discussed last time with the FASTA and FASTQ files. What is the structure of those files? So please pay attention to those details when you solve the programming assignment, okay? And again, we extend the deadline by 2 days, so you have until the end of Wednesday, okay? And especially pay attention if you have any extra lines after every 4 lines. So we cannot guarantee that all the time all bioinformaticians are correct and accurate when they generate those files. So you have to pay attention to those. Make some error handling, some F statement, whatever you like, okay? And one more thing. If you are looking for the ID, normally the ID is separated by a space. So if you're looking for read ID, normally it's separated by a space, okay? So you would read that line, look for the @ sign, and keep checking until you get the space. And that first part will be your read identifier, okay? Okay. So in every lecture, I like also to remind you about whatever we got in the previous lecture, okay? So just to keep yourself fresh and paying attention to the lectures and the flow of those topics, okay? For today, we're going to discuss something very interesting. And this is how you would deal with real genomic data every time you would like to check it. And remember that each of those FASTQ or FASTA files normally huge. It's really huge, like 100 gig bytes. So you cannot check it by your eye and check those lines and start building correlation out of it, okay? The same way, you cannot even open it in your laptop or computer. So you have to have an efficient way of streaming that file. Read it piece by piece, You cannot just open it and load it, the entire thing on your main memory, okay? And that's what we'll be talking about, indexing genomic data. So if I ask you, and this is, again, really real life example, whenever you deal in bioinformatics application, you will face that problem right away. And this picture generated by ChatGPT. So it's nice to use it in those kind of things, right? But don't use it in solving the assignment and exams and so on. So if you are given a few sequences, genomic sequences, and I ask you to find the species that their genome has those genomic sequences. So if I give you this genomic sequence, for example, and ask you, what kind of species do you think this genomic sequence belongs to? Is it a bird, human, cat, dog, whatever, right? How you'd figure that out? And I want to make it more harder. If I don't give you one sequence, I give you a bunch of sequences. And I ask you to figure the origin of every single genomic sequence in your hand. How you do that? We try to see. Reference genome, excellent. So we got some reference genome for some random species that we are aware of, and try to search in every of those reference genome. How hard this problem, computationally? Let's see. Let's give you some insight, okay? So ideally, I would go to something like Google DNA, okay, and go to the search engine, try to paste that sequence, and I ask Google DNA to give me the origin of those sequences, right? But unfortunately, such thing does not exist. There's no Google DNA, right? So we really need such thing where you could search those genomic sequences. So I made that up, okay? If you search, you'll never find it. Okay. The nice thing, we got something called Logan. Logan is a search engine that enables you to look in SRA database. SRA database. What is SRA database? If you remember. Yes, go ahead. Go ahead. Who knows? What is it? Excellent. Which has the sequencing reads. If you remember how you obtain genomic data, we said you could download them, right? And we could download the FASTA files from RefSeq database, for example, right? But we could download the FASTQ from two sources. Which one and which one? Who remember? We have the SRA and we have ENA, right? The American way and the European way. Those are the two main sources where you could download FASTQ files, right? So what Logan does, they build the search engine on top of SRA, okay? They bring the entire SRA database and they enable some way you could look into every single species sequencing reads, okay? So this is something huge. It's really challenging. It's not as easy as you bring some files and you try to index them and that's it. Because the size of the SRA database is about 19 terabytes. You can imagine how hard to index something like that. And they need about 30 million CPU hours to do that. Okay? Of course, you cannot do it in regular research institute setup. You need really huge clusters, such as Amazon Cloud, and they got a grant. They were using the entire infrastructure just to download the data, filter some stuff, and then build index on top of that, and then enable an interface connected to those computing machines so you could access the data. This is something huge, and there is a paper out of it, and the search engine is freely available, so you can access from the first link. The second link is the paper itself, okay? All right, so I did the test myself. So you can search for k-mers of size 31. Why 31? It's their own choice. They choose that, okay? So once you open the link, okay? You go to dashboard, or there's a button to the right top corner called search the planet. Search the planet, okay? And you need to insert your own query, and then you add your email address, and then submit the job. We'll submit to the Amazon cloud, wait for some stuff, maybe probably there's queue scheduler or something, because there are millions of people submitting their jobs. And once it's done, it will send you an email that your job is ready. You can browse it. Once you browse it, you will get those results, okay? What is this? So those are the FASTQ file IDs that you would get, that they contain something similar to this, okay? So you would look for the query, and the tool will give you all the files that probably contain this genomic sequence. And then it's up to you to say whether it's related to this species or that species and so on. But not only that, the tool also gives you the location around the world where in each country they might have that sequencing data. If the sequencing data coming from Japan, you'll get some hit over there. Australia, Middle East, America, and so on, okay? So that's something really nice. Think about a disease like COVID-19. You want to understand or study the origin of those sequences. So you got a variant or a strain, okay, for one of the passenger, and you'd like to know whether it's coming really from China, Japan, Russia, or it's originated inside the country, right? So how you would do that? You need to look for the sources, and those are the sources, and you'll get visualization for the geolocation. All right, so how they did that for 19 petabyte? It's a huge number. How they could enable searching inside those data. Do they go over each data set one by one and try to find that piece of information? Let's see an example. If I ask you the exact same thing, but this time for a very small scale of data, very short sequence, and I ask you to find this subsequence in that long sequence, what you would do? If I were starting with bioinformatics application, what I would do, I will go from first character, start checking, is it similar to that subsequence or not? Do we have A? No, skip. Do we have A? Yes. Do we have A, another one? Yes. Do we have C and C? Oh, there's a hit, right? So that would be the first location where I got the subsequence. And then I will continue doing that. Do we have A? No. Do we have A? Oh, I have A here, another A, followed by C, followed by C, right? Then I start figuring out all those subsequences one by one. Now, if I ask you for another subsequence, I give you another query. What you would do the exact same thing. You would go from the beginning and try checking. Do we have T? No. T, 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 no T, until you start facing those T's, right? And then you go followed by A, and so on. So imagine I give you thousands of queries. How many times you go over the same file? It's too much, right? And that's what we would do. You would scan sequentially that reference genome. Start to look for that query, assuming this is the query and this is the sequence that you are looking inside, okay? Now, computationally, how expensive is this? It's a big O, M, and K. What is M, what is N, and what is K? So the M, assuming is the query length, right? Because I'm examining every character in that, so that's why it's affected by the length of the query itself. And the N is the length of the reference genome, because I'm scanning it sequentially every time I check character by character, right? And how many times I'm doing this? K times, assuming K is the number of queries. If I have 2 queries, I have to scan the entire file 2 times, right? And every time I compare with the query and see every character in there, does it exist? So that is something huge, because I rely on the length of the genome, the length of the query, and the number of queries I have. But also imagine that I allow for inexact match. Inexact match. What does it mean? Instead of looking for the exact subsequence, I allow for some differences, some variation. For example, if I'm looking for Switzerland in a book, I could allow for Netherlands to be a match because it has some similarity between Switzerland and Netherlands, right? So the exact same thing here. I could allow for some inexact matches. Why is that? Because as a human being, we have some differences, right? So not necessarily all the time we look for exact or perfect match. We could have inexact matches as well. And if we want to do that, now the story is different because the way I check the subsequence now is no longer character by character. I should allow for some multiple variations, and that would require quadratic time, which is a topic we call sequence alignment, which rely on dynamic programming that we are going to study in the next maybe 4 lectures or so. Okay, so we'll discuss when we arrive to that topic why we need quadratic time. But this quadratic time is really required in order to check all other enumeration of that subsequence. Whether is it deleted character, is it inserted, is it substituted, and so on. All right, now we already understand that looking inside those data is something really heavily computation. In terms of computation, it's really expensive and would require main memory, would require large storage, would require large number of CPU hours. Now, how we could solve that, how we could do better. I don't know if you were born before the yellow pages or after. Who remembers what is yellow pages? 1, 2, 3. What is it? Phone book. Excellent. So in the old days, very old days, like 20, 25 maybe years ago, we don't have internet. Okay, most of the people don't have computer or don't have access to websites that allow you to find a phone number for someone. And if you would like to access a phone number for anyone in the country or in the state, what you would do, you would purchase that phone book, right? And what you would do? What is the first thing you would do? If you would like to search for a name and then fetch the phone number of that name. Excellent. That's first step. You would go to the last name and pick the first character in the last name, right? And you go to what we call an index, which is the first normally 100 pages or so in that book. And you would look for all surnames that start with that character, okay? Once you figure out the surname that starts with that character, what you would do, you'll go to the next character and look for the surnames that start with now these 2 characters. Then the 3 characters, 4th character, and so on. Or sometimes they just give you the first character in the surname and then give you a page number. If you're looking for all surname that starts with that character, go to that page number, and then you fetch all the surname that start with that character. And then you would do the exact same way. You would go to the 2nd character, 3rd, 4th, 5th, until you get exact match for the person that you're looking for. And then you will get the phone number. And this is exactly how we would do it in real life. We would not go to the first character in that book and keep searching for every character. So in short, this is the yellow pages or the phone book, right? And this is the index. This is where we have the surname. We look for some names, and then you got the phone number for that person. How you do it? You would do it in 3 steps. The first, you will go to the index, get a small portion of the name that you are looking for, and then fetch the page number that belongs to that person, retrieve the pages, and then search only inside those subset of pages. You don't search in the entire book. You search for subset of those pages. And then you match the full name. Of course, here, we cannot use inexact match, right? We should be looking for the exact person that we want to call, right? Imagine you just call some random numbers because you use inexact match. And that's how we exactly will be doing it for genomic data. Now, I have a FASTA file, I have a FASTQ file. And whenever we have a FASTQ and FASTA file, you need to always consider the FASTQ file as a query, And that's why we call it FASTQ. And Q here coming from query, as we discussed last time, okay? So this is always the query that we have. And the FASTA is the reference, is the thing that we are looking inside, okay? So this would be your query, and this is the thing where we will be looking inside and see if we have a match. Now, what we would do? What do we have the first portion of the phone book or the yellow pages? What we call it? An index, right? So we have an index. So we need to build first the index for the yellow pages in order to be able to check the yellow pages every time we have a query, okay? Now, how to build the index? We just get small portion of data from the yellow pages or the book, the entire book, and try to record those pieces. Only those pieces, which is a subset of the reference genome. So we got subset of the reference genome, and we build an index on top of those pieces, okay? Now we store those pieces somewhere, and whenever we get a query, we go to the index first, we check, does it exist? If it exists, we go to another subset in the book. If it does not exist, I'm done. I don't need to look further, okay? Now, whenever we get a query, we will do the exact same thing. So I just extract pieces. So remember, when we were looking for a person to find the phone number in the yellow pages, we got the first character only, or the first character of the surname, okay? And that is the pieces that we are looking for. So we got only subset of the data, and then we try to check in the yellow pages, does it exist or not, okay? And we are doing the exact same thing here. Now, what we call these pieces in genomic, of course, what we call them? We call them a seed, or a k-mer, or a q-gram, okay? So in natural language processing, normally we use that term, q-gram. But there are some papers try to copy that term from the natural or NLP, natural language processing, all the way to genomic, okay? So that's why you might find this term as well in some papers. Now, k-mers, the k here is the length of this piece. If you are picking 5 character long pieces, it means k equals 5, okay? And then we replace the k with that number. So if you are using 5 characters in every piece, we replace the k with 5, and then the term becomes 5-mer, 5-mer, okay? Likewise, if you use 6 characters, you call it 6-mer, 7-mer, 3-mers, and so on, okay? So be careful that the k here is just the length of the subsequence that we are looking for, all right? Now, there is fundamental difference between seed and k-mer, although they have the exact same name. And we are going to visit that or revisit that toward the end of the lecture. So pay attention to that. There's a little difference, sometimes creates confusion between the seed and the k-mer, okay? If I forget it, please remind me. It's a very important difference, okay? Now we extract some seeds or k-mer from the first reference genome. We extract some k-mers from the FASTQ file. Now how we do the search? So we would like to see, does this file contain any of those blue pieces? We check. Do we have blue pieces here? We have 1 and 2. That's great. Okay. Sounds like we could have something. Let's move on. Do we have green pieces? How many? Excellent. So we have something to work with. So we have 2 blue and we have 2 green. Now how about the red? Do we have red pieces? How many? We have 2 also. That's excellent. Okay. Sounds, I may have some head. And this is exactly how Logan works. Okay. Now, when I'm looking for something, I expect to have the exact same order of those pieces. So I have the blue followed by green, right? Followed by red. And that is logical way of thinking to expect the exact same order in the file, right? Now, instead of looking in each of those pieces individually and see, do we have blue, green, red? That is not going to give me something because it might give me totally random subsequence, right? So now, instead of looking for each of those pieces separately, I'm going to look for a group of pieces together. Do we have a blue followed by green followed by red anywhere here? Where is it? In the middle, right? Excellent. So I have here the blue followed by green followed by red. Now this is going to give me a very close nearby similarity between that portion of this file and over here. Now, instead of having two possible options, I have only one, right? Do I have any other alternative? Do I have anywhere blue followed by green followed by red? No, right? So instead of looking randomly, I got 6 options because I have 2 blue, 2 green, 2 red. Now I have only one location to look further inside, right? So now I reduce the search space from the entire file into a very narrow portion of the file. Now, whatever computation I use, even if it is the most expensive one, the workload itself, it's still minimal, right? That's why it's very efficient to search in huge data, regardless the size. And what you guess is correct. That is the location that we are looking for inside the file, okay? Hopefully this is clear. You understand the concept of how we look for those pieces, okay? Now let's jump into the detail of that algorithm, okay? We already told you to pick some pieces, but we never discuss how to pick those pieces. Is it randomly? What is inside them, okay? Do we need just to get a piece of character altogether? Can we pick some of them? Can we pick every other piece, or we will pick overlapping pieces, non-overlapping, and so on? We will see all of that in the coming details, in the coming slides. All right, now let's give a formal definitions to the things that we were discussing, okay? We would have 2 important terms called indexing and seeding. Indexing and seeding. What is indexing and what is seeding? First, those 2 steps help us to quickly locate subject data without having to sequentially search the entire data. Hopefully this is now clear to us. What do we mean by sequentially searching that file? And what does it mean to save us from doing that, okay? Now, the first term, indexing, stores short subsequences, which are the thing that we call seeds or k-mer, okay? Extracted from the target genome, which is the FASTA file in our example. But remember, we could also have a FASTQ file as a query and another FASTQ file as a reference, okay? And we would get queries from one file, look for the other file inside it, okay? We could do the opposite. We could have a FASTA file as a query, and we look inside another FASTA file or FASTQ file. So it's up to the problem that we are handling, which one is a query and which one is a reference, okay? So now, indexing, first, it extracts short subsequences, okay? From where? From the reference that we would like to look inside. Remember, this is a big difference and fundamental. So we are looking always inside the target genome. Again, regardless if it's FASTQ or FASTA, it doesn't matter. Wherever we are looking inside, that we need to build the indexing step, okay? Seeding is for the other side of the story. Whenever we want to have a query, we do seeding, okay? Whenever we want to look inside something, we do indexing. Hopefully those 2 terms are clear now, okay? Do we have any question? So seeding, we do it to the file where we have queries. Indexing, we do it to the file where we want to study inside or looking for a piece or a query inside it, okay? Now, both of them should use the exact same algorithm. Both of them should use exact same algorithm. Means that the way you pick those pieces should be exactly the same, okay? The number of pieces from certain region or certain length should be exactly the same. If I have 100 long character, if I pick 4 seeds from that 100 long, should be both of them exactly the same from the query and from the reference genome, all right? Now you can think why we should use the exact same algorithm. Imagine that I'm comparing apple to banana. Doesn't make sense, right? Imagine I pick just the first piece of information from one sequence, and I pick the last piece from one other information. How I could match them? Doesn't work, right? That's why the exact same way I extract seeds should be the exact same way I extract seeds from the other way where I want to look inside, okay? Now, the only difference that in indexing, I build what we call an index, okay? In seeding, I don't build index. I just use those pieces to look inside the index. So over here, we will build index, and that we'll be using for the yellow pages. Remember, in here, we don't need to build the index. We just extract those pieces, use them as a query, and look inside the index of the indexing step. Okay? Hopefully this is clear. We spent already some time on it, but this is where we do the indexing. Those pieces should be stored somewhere. So next time when we get a query, we extract the pieces using a seeding mechanism, and then use those seeds to look inside the index we built in here. Okay? Those very important terms, and I spend some time on them because we are going to reuse them on almost all next lectures. Okay? Indexing, seeding, seed, and k-mer. Those are very important terms. All right, now let's see how we do the indexing. So we got a reference genome, regardless, again, if it is FASTA, FASTQ, whatever. Those are the things that we would like to search inside, okay? We need to build indexing. We extract, using some ways, some algorithm, those pieces, and we need to store them somewhere also. Now, where do we store them? Think about ways that enable us to search inside them in very quick time and very short memory requirement. What are the data structure that enable us to look inside them? You give it a query, give you responses whether this query exists, in which location, and so on. So one of the example could be a database, right? Where you store all of those pieces and you store their location along of every piece, right? There are a lot of ways to do that. So we already discussed it in our paper called Technology Dictates Algorithm. One of the most popular way to do that called the hash table. A hash table, okay? What is a hash table? Probably have a slide for that. Yeah, we will see it. But remember, since 1988, okay, the most popular way to store those pieces is still hash table, or what we call hashing. What is it? So you can imagine as a table, okay, table of two columns. I have a table of two columns. In the first column, what do we have? The piece itself, the subsequence that we extract, or the seed. So this is seed 1, okay? What do we have in the other location? In the other column, sorry. We have the locations. The locations of what? The location of the first character in that piece, in that seed, okay? So think about, we have this word or this sentence, and then we extract the very first piece out of it. So this is starting from character 1 all the way to 10, for example. So we pick the first 10 characters. Now, what is the location of the first character in the original sequence? It is 1, right? But in computer science, we always start from 0 because 0 is a thing, right? 0 is a storage, is a location inside any storage medium. So that's why we convert it to 0, and we record here a 0. A 0 means the first character from the seed starts at that location. And of course, since we use k-mer, so k is already well defined, so we already know it. If it is 10, then it means all the seeds have a length of 10, right? So we start from that location, and we move forward for 10 steps to get that seed back, okay? Now, do we have any green? No. So that's it for the first row. Now we move to the second seed. It's a blue, right? If this is 10 character, then what is the location of the first character from the blue piece? 10, right? So we have from 1 all the way to 10, right, here. And the next piece starts at 11, right? But because this starts from 0, so we shift everything by 1, then the location should be 10. So excellent, 10. So now we'll have the C2, which is the blue one, and the location should be 10. Okay? Remember, we already know the K value. So that's why we could safely record only the location of the first character, and we could build back our sequence only from the hash table, because we know at this location, move forwards for 10 steps, you will get C2. Okay? Now, do we have another blue piece? Yes, we have it over here. So don't move to the next row. We're still in the second row. Every row should have a unique seed. Okay? You cannot repeat those seeds in the hash table. So if you have any occurrence of C2, you should still record it in the same row. Okay? Now, the last row, assume the length of that sequence is 100. So the very last piece is blue again. It means we go probably to 91. That is the location of the last seed in the sequence. Okay, maybe. Depends on how many seeds we have on the way. So I'm going to deduct 1 because we start from 0. Then we have also at location 90 the exact same seed, okay, because both of them are blue, right? Now we move to the yellow. We do the exact same thing. Do we have any other blue? No. So we could move now to the next row. Don't ever move to another row if you don't know if you have that seed or not. Again, this column should be unique. Okay, there is no repeated entries. Now we'll have the seed 3. Probably I should use color here. I should call it maybe yellow instead of number, so you don't get confused. Now we have 2 of them. Assume, for example, this is starting at 20 and maybe, I don't know, 80. Okay. Do we have another yellow? No. Move to the red. Seed, red. We have 1 of them, so let's have just 30 maybe. That's it. Very simple way of building the hash table. Okay, you should all be able to build that. Just 2 arrays, or you can think about a 2D array where you have 2 columns, and you can visit those by index. You could have some way of indexing this. But there's a trick when you build the hash table. Why we call it hash in the first place? Why we call a hash table as a hash? Why would just not call it table and that's it? So hash is a function. Hash is a function. We always use this character to denote for a hash function. And when we say hash of seed 1, it means I want to convert this subsequence into something else. Okay? So hash of seed 1, for example, equals 123, for example, just a number. How we calculate that number depends on the hash function that we use. Normally, hash function has some multiplication, division, and so on. It's really a mathematical equation, okay? Just take the first character from here, do something, some operation, the second character, some other operation, third character, and so on. Multiply them together, divide over some numbers, and so on. There are a lot of studies on how we can build efficient hash function, okay? There are a lot of them, different ways of how we choose hash functions. Now, why we convert the seed into a number? Why not just keep the row subsequence as is? Why we convert a text into a number? Now, let me give you some insight. Regardless the length of the seed, I'm going to always get the same number of digits in the number. If this is 1,000 of characters, I'm still getting 1, 2, 3, 4, 5 characters, 5 digits of number, okay? If this is 500, I'm still getting the 5 digits. If this is 2 characters, I'm still getting the 5 digits. Okay? That's one of the properties of the hash function. Now, what kind of benefit this is going to provide? think about, you have one software you develop, right? But you have many input. The user is going to choose the K value he likes, right? It's just a parameter that you provide from your software, and he's going to enter 10, 20, 300, 500. Now, if you build your array in a fixed size of character, what will happen? It won't work, right? Because you fix the size of the array into K equal 10, for example, because it should be predefined when you build the index, right? When you build the array. Now, the user choose 20, and your array allows only for storing 10 characters, not 20. Will your software work? No, right? But now, if you build your array for those 5 digits of number, what will happen? Regardless the K user used, right? You're always able to handle whatever K you choose, right? Because you're going to always store those characters. Okay? So that's one way of dealing with variable K length. So whatever the user choose, 20, 100, 10, 2, 5, still you're able to build the index without any error. Okay? That's why we use hash function. We are going to give you an example of this hash function, how it works, if you're interested in. Okay? Now that's all for the hash table. Of course, there are some other important properties. Now it's a number. Sometimes the hash function going to provide the same exact number for 2 different seeds. Sometimes the hash function, okay? This is mathematical properties. How many of you from math department? 2? Okay, excellent. Probably you already studied this somewhere. Probably you already studied that. We call it a collision rate. A collision rate for the hash function. Collision rate means how many times I'm going to get the exact same number for the 2 different seeds or different seeds. Okay, if I have 10 different seeds, will I get the exact same number for all those 10 seeds, or 5 of them, 4 of them? Okay, if I get the same number for multiple seeds, that means something bad, right? Because I'm going to look for those pieces, and the hash table going to give me information that they exist, right? Because when I look in this array, I find them over here because I get the same number, and then I search, does this number exist here? Yes. Okay, means the seed exists. So that's going to give me wrong information, some false positive. Okay. So those things like external stuff, so don't worry about them. They are really technical details. So they are not part of the lectures. That's why I'm explaining them here, not in the slides. But if you are interested, since you are from math department, those things would be nice for you to understand and check research paper about them, which is the collision rate of the hash functions and how to build an efficient hash function that provide you the optimal number of digits without wasting the storage in this array. Okay. Right, now assuming we build the hash table out of the things that we would like to look inside. Okay, remember the hash table or the index for the things that you would like to search inside. Okay, now we finished the hash table, we got the query. Which step we need to perform for the query? Indexing or seeding? When we got the query, do we need to perform indexing or seeding? Seeding, excellent. So when we got the query, we perform seeding. And now what we need to do is the seeding step. Seeding is just extract those pieces. The same way you do for the hash table. So you would go to the first character, for example, pick the next 10 characters. That's it. That's seeding, done. You don't do anything extra. You don't build hash table. You don't record the storage location. But if you convert the seed into hash value in the hash table, you need to do that in the seeding. Why? Because you no longer have seeds, you just have numbers. And when you would like to search those numbers in the table, you should have numbers to look for, right? So you convert that seed using the same hash function. So hash seed will give you a random number, maybe 5364. 5 digits again. And then you use that number to look inside the hash table. Do we have that number anywhere in the rows? If you have it, then you fetch the location. Okay? All right? Now, of course, a very good hash function, whenever you have the exact same seed, it should provide you the exact same number. Okay? There are two things. There are the exact same seed should always give me the same number. And there is the other thing, the collision rate. Whenever I get two different seeds, not the exact same seed, two different seeds, I will also get the same number, which is bad. I don't want such scenario to happen. Okay? But when I have this exact same seed, I should be always able to get the exact same number. That's something I want. But when I have two different seeds, I don't want to get the same number. Okay? Hopefully now everything is clear about seeding and indexing. Yes, please. Excellent. So now, if you want that as a property of your application or software, you would change the hash function. You would use a hash function that allows for some collision rate. Okay? You would use a hash function, but remember, collision rates sometimes happen randomly. Two seeds, totally not similar to each other, and you still get the same number. You don't want that. That's why developing a hash function is still active area of research. It's very tricky how you enable hash function that do certain properties that you are looking for. For example, you are always looking for the second character to be anything. You don't require the second character to be exact match. For example, this is your software. It's up to you how you define the requirements. Now, assuming you had such requirement, for example, let's say you have G and then something else, G, 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 okay? G means here, you want an exact match, for example. But the X means I don't care. I don't require anything. So whenever I have, for example, T, A, T, T, I need that to match with T, for example, C, T, T. If I got such cases, my software should define them as exact match, although they are different. But for me, I don't care about this character, okay? Assuming this is my application, this is my requirement. How I would implement this and how I would build a hash table for that. Any idea? If I really don't care about the second character. Now, first thing is to develop some hash function, which math people are really good in this thing, how you develop hash function that provide me a number out of this by ignoring this. That's one thing, one direction, to build a hash function that's specifically doing that. The second thing, just ignore that character from the seed. Just delete, pretend that does not exist at all, okay? Just delete it. And now store this seed in the hash table. Whenever I get any seed, delete the second character and store that seed as is inside. So when I store this, it will be no longer 5 characters, it will be 4 only. So it will be T, E, E, T. Now I'll save this in the hash table. Now next time I get a query, assume it's T, A, E, T, or another query, T, G, T, T, T. So every time I get a query, I also delete the second character. This becomes T, 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 T. And then I search inside the hash table for that query. Does it exist anywhere? Yes, because I just store it, right? Then I get exact match. This way, I allow for an exact match, although I'm using exact match hash function. I didn't change the hash function, okay? So those are two ways to answer your question, okay? But this is an excellent question. It's really important. Sometimes we got some application in genomics that we really need to allow for that inexact match, okay? All right. So hopefully everything is clear about indexing and seeding. If you have any question, this is the time to ask. All right. Let's see in practice how we pick the seeds. Until now, we randomly talk about seeds, extract them from somewhere. Could be from first character to the next 10 characters and so on. Let's see different ways to choose the seed itself. Now, if you check the literature review, how many of you picked the review paper for seeding? Read mapping? Read mapping. Okay. You might go over that topic, the seeding, how you pick the seeds, or what kind of indexing they use. Okay. Especially if you pick tools that they have totally different indexing mechanism. You might see something called BWT, Bors-Wheeler transformation. Bors-Wheeler transformation, which is different from hash table. This is another way of how you build an index. Okay. There are some other structure like trie tree, for example. There are also suffix tree. There are too many ways of indexing, okay? But those are the most famous. The top famous one is hash table, as we said, since 1988. This is the most popular one, okay? The second popular one is the Bors-Wheeler transformation, okay? BWT, sometimes with FM index. Bors-Wheeler transformation with FM. But regardless of that, what kind of algorithm we could use to pick those seeds? So we have really different mechanisms to pick those. For example, the first one is just do overlapping. You got the sequence, you just pick all overlapping from first character to 10 characters, second character, next 10, third character, next 10, fourth character, next 10, and so on. So really all overlapping seeds, just pick all of them, okay? Now, how many of them you would be generating? At every character, you pick the next 10. So if you have here 100 characters, then you would pick 100 of them, right? However, toward the end, for example, this character, last character, you cannot pick next 10, right? At the second last character, you cannot pick next 10 because there are no remaining characters, right? So toward the end here, you would be able only to extract single seed instead of continuing this way. You cannot continue, right? So there are no more characters to extract here. So toward the end, we'll just extract one seed. So that's why we said n minus k plus 1. N character we have in here, minus k for this one, plus 1 to adapt for the last character we have in here. Okay? So that's in case of overlapping seeds. We have n minus k plus 1 seeds to extract. Now we could also have non-overlapping. What does it mean? And does any one of you needs the drawing here? Did I erase? Okay. This is very good quality. We can erase it. All right, so non-overlapping, what does it mean? Think about you have a reference sequence. I want to extract all non-overlapping. So I go to the first character, extract the next k. Now, what should be the second one? None of these characters, as simple as that. None of these characters kept, and then start from here. Skip, start from here. How many of them? Adapt for the toward the end, something, right? So we'll have n over k, maybe deduct something toward the end, okay? Yeah. And then, of course, make maybe ceiling or floor, because you want to have it as exact number, right? You cannot have fraction for number of pieces, right? So this is way less than what we have over here, right? This is non-overlapping. Now we could have spaced. What does mean spaced? Spaced is the thing we discussed, the inexact match, inexact match. For example, I have this exact same reference genome. Now, spaced could be for overlapping, space could be for non-overlapping, doesn't matter. Spaced mean instead of picking this k character, you ignore some of them. You ignore 2 characters in every seed, for example. That is spaced because you allow for some space within the character. That's why we call space. So if you allow for 2 characters, you should allow 2 characters in every seed, the exact same location. Okay? So you still get the exact same number of seeds. It won't change the number of seeds, but it will change the content of the seed. You could apply it also, where's the overlapping? Yeah, you could apply it to the overlapping seeds. So every seed, you just ignore some character. It should be the exact same location. If you ignore every second character, you should do that, okay? Now also here, you should ignore that character. Now you apply space to non-overlapping and space to overlapping, okay? That's what do you mean by space. Now adjacent, what do you mean by adjacent? Next to each other. Next to each other, it means whenever I end with this character, I start with the next seed. And with this character start, which is exactly this example. Non-adjacent means allow for some gap between the seeds. So instead of doing this, we force it. We force it. So we pick the first seed from the first K character. Okay. Now it's up to me. I choose a gap of 2 characters. So every time I choose a seed, I ignore 2 characters after that seed. Ignore this. Now extract seed from here. Ignore 2 characters. Extract seed from here. Okay. Now this is a gap. This is 2 character wide. And this is 2 character wide. This is 2 character wide. Now how to get the number of seeds I extracted from here? We said n over k, right? You remember? Now we will do n over k plus 2. Because this is now you can consider as part of the seed, right? Which is similar to spaced seed, but we ignore the last characters. So we ignore the last characters from the seed, and then we continue with non-overlapping, right? So now we have much less seeds than what we have in spaced and non-overlapping and overlapping. So if I ask you a question, so far, out of this method, what is the method that produce the least number of seeds? Non-adjacent seeds, okay? That's one of the mechanisms that we could use to extract the minimum number of seeds, so far. There are other methods called syncmers, stropmers, genome on diet, non-adjacent, minimizer, compressed, and so on. There are really large number of methods how we pick the seeds. And hopefully, over the next 2 lectures, we are going to continue with this topic and see some of those in action. Today, we will go over 2 methods, and we will continue next lecture with other methods, okay? This is a very important area of research, okay? It's not about how you choose. You could choose randomly how you pick your seeds, but you have to demonstrate, you have to prove that these are working methods. For example, if I give you an query that I know it's already exists in this data, and your method using those seeds find that piece of information or not? It's not always good to pick minimal number of seeds because you could lose some of information. You could not find them, okay? So it's not always the least is the best, okay? And you can see that from this method. Those are the name of the tools, BWA-MEM2. This is state-of-the-art tool. You could use it. Mr. Fast, this is no longer in use. Minimap2, state-of-the-art tools. BWA-MEM, no longer used, replaced by this. Genome on Diet, this is my own tool. We just published this here, I think a week ago or so. So now, if we have the index size and the indexing time, what does it mean? Indexing size is the hash table itself. You remember the 2-column thing? That's the index size. If I build 1 terabyte hash table out of 3 gigabyte genome, is that something good or bad? Of course, bad. It won't allow me to search for large data, like the 19 terabytes of data, right? Or peta. It's not tera, right? It's a huge, the SRA database. So if you check the index size, you see really differences between the different methods. Some of them, again, all of those for the the human genome, which is 3.2 gigabytes. Okay, so I have 17 gigabytes coming from 3 gigabytes. So I have reference genome of 3 gigabytes, but the index I build on top of that is 17. Not only that, the peak memory, 72 gig. The peak memory is the main memory I need for the machine to run that algorithm. Okay. So that is what I'm going to store, which is the hash table. But the software itself, to build that, I need a main memory of 70 gig. The indexing time is also different. Now, which one is better? We cannot always say genome and diet is better because the index size is the minimal and the indexing time is the lowest. This is not the only important factor. What's important, again, as I said, if I give you a sequence and I know it exists in the data, can you find it or not? If you build the minimal hash table and you are not able to give me that sequence, and I know it exists in the data, that's something wrong. Okay? All right, now let's go in details into the first method called overlapping seed. We already see something out of the overlapping. We discuss it, but now let's see some advantages and disadvantages of this method. This is the first lecture. I moved the camera a bit. Yeah, I cannot see myself. So every time I was putting it here, so it was recording my back. So I tried to do something. Normally, we should face it somewhere here so you can see the wide angle of the class. But because it should be connected with a wire, I cannot do that. So I have a clicker, so I could move the slides from here. So maybe I should place the laptop somewhere there. Then I can place the camera over there. Or your colleague suggested that we use the room camera. We have a nice camera. I tried it a few minutes ago, and it really could track me. So it could go with me automatically. So maybe we could consider that next lecture. If you ever used this equipment before in any of your classes, let me know. I know most of you are PhD students, so you work as TA for some courses. So let me know if you were exposed to using this instrument before. Yeah, I would do that. I would do that. All right. So let's go over overlapping seeds. What do we mean by overlapping? Is this way. So we have a reference, and we extract every overlapping subsequence or seed. Okay. Remember to ask me about the difference between a seed and k-mer in the next example. All right. Now we have two sequences. Think about S1, and S2. Okay. What is the difference between S1 and S2? Is only that little character, the C. Okay. We do one difference, which is replacing the G over here. Okay. We replace the G with C. All right. Now let's extract all overlapping seeds between the two sequences. We keep extract. K here is 4, so this is 4 mer. Again, remember the K you could replace it with a number, and then you write mer. 4 mer. Okay. Now we extract all 4 mers from this sequence. We extract the first 4 characters, we shift by 1 character, and then extract the next 4, shift by 1 character, extract the next 4, and so on. Keep doing that until you arrive then. And we said how many of those we could extract? N minus, okay, where are the math people? N minus K plus 1, right? Those are the number of seeds you could extract from here. N is the length of the sequence, K is the length of the subsequence, and plus 1 to adjust for the last character, okay? Now, remember, we did just single difference. We replaced the G with the C. Now let's extract the subsequences the exact same way, and we will get N minus K plus 1 subsequences. Now, when we compare what we got as a seeds over here, what we will see? We will see some of them are matching and some other do not match. Although just single difference, but how many of them do not match? 1, 2, 3, 4. 1, 2, 3, 4 do not match, although we have single difference. Can you relate the 4 with the 4? And that's exactly what we will get in real life. Every single difference going to affect K seeds, okay? K seeds. Every single difference going to affect K seeds. So if you have that idea in mind, now you could build efficient algorithm that can compare two sequences by their k-mers. Can extract k-mers and quantify how many of them are similar to each other, okay? Just quantify. If you got, for example, 20 from the first sequence, 20 k-mers, assuming 20 k-mers, and you got from the other one 20 k-mers, and only 18 of them match. How many of them, can we say something about the number of differences between the two sequences? If I extract 20 sequences and I got only 18 of them similar, can I say something about the number of differences? About 16. Can I say something? How many differences do I have between the two sequences? How many? Raja? 4 differences. I'm talking about differences in the sequence itself. How many differences I will have between the two sequences? One. How I could calculate that? So K is 4. If I'm missing 4 of them, it means I have 1. So for every 4, I'm missing at least 1. For every 4, I'm missing at least. Why at least? If it happened to be the two differences in the same k-mers, then I'm still getting 4 of them get affected, right? So that's why the minimum number of differences is affected by the number of k-mers that are different between the two sequences. So every 4 differences equivalent to at least, at least 1. Okay, at least 1. So in this scenario, yeah, 4 of them equals 1 or leads to 1 difference. But if I have 2 differences in here, for example, the A also replaced by T, do it yourself, you'll find also 4 k-mers are different because it happened to be in the same k-mer, okay? So that's why we said at least, not equals. At least, because that region, all of them overlapping, so we expect K of them to mismatch. Okay? That is an efficient way of comparing the two sequences. Now, you could ask yourself, why we extract those subsequences? Why not just comparing this sequence with that sequence and that's it? Why not just going character by character and done? Why we need to extract all these subsequences, store them in a hash table, and then query them and quantify them? This solution does not scale. It works, yes. You could implement it, yes. You could do for loop and go over the two sequences and check character by character. Does it match, match, match? If no match, you quantify that, and that's it, right? But this solution does not scale because you are going sequentially, one by one. If it is million long, you would need million iteration to finish the calculation. If it is 100 million, then you would need 100 million. So it doesn't scale, right? However, this solution scales really well because all the time you extract this k-mer, you store them somewhere. Next time you get a query, you just revisit that hash table, and much faster you could query all of those. Much faster, okay? It's not only about overlapping, the exact same thing applies when we use other methods. So in this way, maybe we extract excessive number of seeds, because large number of seeds, right? But next method, like non-overlapping, extract way less than those seeds. So easier to handle those less number of seeds rather than handling the very long sequence, okay? All right, now let's see another example. The exact same sequences we had, Remember, we replaced the G with the C, right? And then we extract all non-overlapping, but this time we choose a K of value 6. A K of value 6. So now what we call it as 6 MERS. Okay, right? Now what happened with the number of mismatch seeds? We had those as exact match, those as exact match, but those mismatch. How many of them? 6, right? So you can see by changing the value K, we expect to have more mismatch seeds. Now, if I use it as 8 or 9, maybe none of them will match. None of them will match. And that's going to open an important question: what value of K should I use? Now I have a single difference between the two sequences and none of the seeds match. None of them. That's crazy, right? So your algorithm is perfectly fine. Your idea works well, but the value you choose for the parameter doesn't work well, right? That's why we have to be careful, not only about the method we choose, but also about the parameter value that we introduce to the tool, okay? So this is very important thing we should discuss whenever we deal with those tools. Okay. Now we finished the similarity check. We have two sequences that are really similar to each other, and we have one difference. Now let's get totally different sequences. Totally different sequences, okay? They have large number of differences, not single difference. And we use 4 MERS, okay? 4 MERS. Again, we're still in the non-overlapping example. We are discussing non-overlapping algorithm, okay? Now we extract all the overlapping seeds, extract all the overlapping seeds. Remember, the number is n minus k plus 1, okay? N is the length of the sequence, S1 and S2. Now, remember, the two sequences are totally different, dissimilar to each other, okay? But we still get some seeds matching between the two groups. That is another pitfall of the algorithm. Although they are totally different from each other, but we still get some matches. So when you build your tool that detects the number of matching seeds and mismatching seeds, you could still give me a false positive, telling me that this is matching each other because I have large number of matching seeds, although they are just false. False matching. This does not belong to the first region. None of them actually match with the corresponding seeds over here, but they match to something else. And that's, we had this scenario in real life. Why? Because we didn't discuss this before, but if you read the paper I assigned to you about hi-fi reads, if you remember, called The Complete Human Genome, which is published in 2022, right? They discuss about 50% of a human genome is just repeated regions. Repeated region. What does that mean? It means if you have the human reference genome, 50% of the content is just repeated somewhere else. Okay? It's not as single portion, but rather you'll see something in chromosome 1 similar to chromosome 10, something in chromosome 11 similar to chromosome 2, and so on. If you quantify those pieces together, it will account for 50% of the total human genome. That's why those repeated region, for example, can we identify the repeated region over here? Probably it will start from the first over here. I would expect the first over here to be similar to something in the middle. That's why the group of seeds coming from the beginning, similar to something, a group in the middle, right? So we have the exact same portion of the sequence over here coming from the sequence in the middle of the other sequence. And that's what we call a repeated region, okay? And giving that information for human genome, so you cannot just rely on quantifying the number of seeds between the two sequences and that's it. This is a big challenge when you want to develop something related to overlapping seeds. However, as you are all smart people, you could come up with a solution to solve this problem. What kind of solution you might expect that will solve this issue? Think about this group is matching with that group. Now, how far this group from that group? So the solution is very simple. Instead of comparing all of them to all of them, which of course, by just random chance, by just luck, some of them will match because I'm comparing apple to banana, right? This is not relevant to the last one. Why I'm comparing the first over here to the last over there? Doesn't make sense, right? Because I'm comparing two sequences and I assume should be some similarity. So I should compare the subsequences in the beginning to something in the beginning and something toward the end to something toward the end, right? So the solution is very simple. Just dictate the search space that you are looking for. So every 100 k-mers, for example, try to compare them with every other 100 k-mers. Or every 3, compare them with every 3. Okay? Now the next 3, quantify, are they similar with the 3 over here? And then move on. Are those 3 similar to that? Are those 3 similar to that? And so on. Now this number of 3 or 100 is also variable and depends on the accuracy, because you can think about you have and just little insertion over here going to shift all the preceding characters. When you have insertion or deletion, it's going to affect all the characters. So even if this is exactly matched with this sequence, if you just insert a character in the middle, it's going to shift everything to the right. And now the k-mers will be shifted as well, right? So you have to account for those shift effect. Maybe next lecture, we're going to take example with insertion and deletion. This lecture, we took only example of substitution. We replace one character by another, and you see what kind of problem we got just by replacing one character. Maybe next lecture, we'll go over insertion and deletion and see how that's going to affect the problem. All right? So if you're interested in this solution that I discussed last, there is a tool called QGram. It's a very old tool. It's really old. I think 30 years old or something. And there is another thing called Ngram. And there is a recent updated version of it called Grim Filter. So if you're interested in this topic, I would recommend you to check those 3 papers. If you want the exact title of the paper, feel free to send me an email. I'll send you the paper. Probably we'll discuss it over the next few lectures. So we will continue with indexing for, I think, a week or 2 weeks. We'll try to cover as much as possible out of those algorithms, how it work. And then we will have the second programming assignment. I'm going to ask you to implement one of those algorithms. It's really easy, very straightforward. You will have a for loop, just extract seeds, depends on the algorithm I will describe for you. If it is overlapping, straightforward, right? And then you're just matching those seeds together between 2 sequences. As simple as that. Just for loop, extract those seeds, store them somewhere, and then you query them. Okay? We could stop for today. We got a lot of information. Yes, please. Excellent. Thank you. All right. So now we have a term called seed. We have a term called k-mer. What is the difference? In theory, for the non-overlapping seed, both of them exactly the same. Exactly the same for the non-overlapping. Okay. But now, yeah, please record your name and your name. Okay. Maybe you can write it now before I forget and have a piece of paper. Imagine I have algorithm that extract all overlapping. Okay. Right. So I would call each of those as a seed, and I will call them each of them as a k-mer. So both of them as k-mer, and both of them are seed. Now, imagine for some reason, I decide to not choose this one. Okay. Now, I already extracted, right? So it fall under k-mer because the length is k, right? So I would call all of these k-mer. However, not all of them will be stored in the hash table. I'm going to ignore some of them. I'm going to keep some of them. Now, the things I'm going to store in the hash table, I would call them seed. Because those as seed. When you plant, you put a seed and result in a tree, right? And exact same thing here. You have a seed stored in the hash table. Whenever you got a query, you are going to use that query to check with the seeds, not with the k-mer. So anything you store in the hash table, I would call a seed. Anything you extract from the sequence is a k-mer, regardless if it is seed or not. Just a k-mer, okay? Subsequence of length k, right? That is the difference between seed and k-mer. In non-overlapping, we didn't see it because all of them are k-mer, right? All of them are seed. All of them will be stored. In the next topic, which will be minimizer seed, we're going to choose some of those. So the things will be stored in the hash table. Let's call them seed, okay? And everything we extract from the genome, we call them k-mer, right? Now, maybe that is my own understanding, okay? Some people might define it in a different way. However, there's always confusion in genomics. For example, alignment and mapping. What is the difference between alignment and mapping? And that's a question for you. When you build your own review paper, you need to discuss these two things. We already discussed it in our paper called Technology Dictates. Dictates algorithm. Okay, which is, I think we have it somewhere. Yeah, this one. So we discussed the exact difference between the two terms. They are very important. Okay, maybe someone does not agree with us. Yeah, maybe they have different way of thinking about alignment and mapping. However, because this area really quickly get developed over time, starting from the 70s or 60s or even 50s, when we start seeing the first chromosome ever for some of the bacteria, E. coli and so on, until today, the technology is getting different. So when we talk about some terms in the past, they are not applicable today. Because simply the data is different, the problem that we are dealing with is different, and the equipment that sequencing those data is also different, right? So when we talk about alignment in the old days is no longer applicable to these days. Okay? Those what kind of confusion you might have between old people and recent generation. Okay? Likewise with the Q-gram. So Q-gram is a term coming from natural language processing, okay? Where you compare, for example, a book to a book, just a text to text, okay? They use that term very often. Now in machine learning, what do they call it? What's the equivalent term for Q-gram or seeds? In AI, ML, what is the equivalent term for the subsequences that you extract from some data and then you train the network over those data? N-gram maybe, yeah, but they have something else. What kind of things you extract? Features, excellent. They call it features or embeddings, okay? Embeddings or feature. They are equivalent to Q-gram, k-mers, or seeds, right? They are the important thing that we extract and we store somewhere, then we train the network on them, and then we use equivalent embedding or features from the query, and we use them for inference, the exact same way. So you can see from different perspective, from different research field, we have different terms, but at the end, they are exactly the same thing, okay? All right, let's stop at here. And we will continue with the other algorithms with the next lecture. Do you have any question? We can continue with the question. We have about 5 minutes or so. ID for the FASTQ. Okay. Yeah, this file is very old. And if you check the slides, I also add a white rectangle here. This is a white rectangle because in the very old format, they used to have a duplicate of those two lines. So this line is just duplicated here. Exact same line will be duplicated here. So I add the white box myself. So in the exact same in the first row, in the old format, they don't have space. Okay? So there should be some space here, separating the read ID with everything else. Okay? If you don't have it, you could assume any delimiter, for example, which could be underscore, dash, slash, any of those special characters, you could consider as separator between this and this. However, if you consider only the space, I'm fine with that. If you consider the first space as separator between the read ID and everything else, I'm fine with that. If you want to go the extra mile, consider all delimiters. Yes, you could do that. Okay, if you consider delimiter, yes, you can do that as well. You can consider NG, but the correct answer is the whole thing over here until this. Yeah, this is the ID of the genome, this entire thing, okay? It's okay. Since I didn't specify what delimiter to be used, you don't have to specify that. It's up to you. You want to consider the first space, or you want to check for all delimiters. That's up to you. But what I want to understand from your code that you are looking for the first portion of that line. I don't want you to look first portion of that line, or that line, or that line. Okay? Yeah, exactly. And I didn't ask about FASTA, so you shouldn't deal with FASTA. Just read the FASTA file, and that's it. Just show me that you're reading, this is the ID, this is the genomic sequences, and done. Exactly. Take the everything, for example. Exactly. No, no. This is just a recognition that this is an identifier line. This is not part of the ID. The @ sign is not part of the ID. This is just a sign to let you know that this is the line related to the identifier. Okay? Exactly. Exactly. Yes. For the submission, I asked the TA to handle it on iCollege. He should create assignment. I don't have really good experience with iCollege, so I asked him to find a way to submit the code and to be convenient for him to grade. Okay? So he will handle that probably today. He will post something for you. But remember, we extend the deadline 2 days more, so you have by the end of Wednesday. If you really need more time, I'm open to it. So please discuss it with me, and we can extend more. But the assignment is really easy. It shouldn't take that long. Okay? Don't use any of the AI tool. It will be really clear to detect that. Believe me, any source code you get from ChatGPT, there is a way to identify that. Okay? Again, the goal of this course to make it really easy for you. I want the most important portion of the code is to get practical side of those algorithms. Okay? So we have the other course, which is related to the theory of bioinformatics. Now, this is advanced bioinformatics, should focus on the practical side. You should be able, by the end of the semester, to develop a read mapper, as we discussed. Okay? So please try to do it by your hand. Try to suffer a bit. And if you face any problem, just discuss with me. Okay? All right? Yes, please. Excellent. So that's up to you. So I told you, and the things we discussed in the lecture was up to 40, if I remember, or maybe 50, right? You could extend that to 70, right? And include the lowercase character. That's up to you. If you don't want to do that, just convert everything into uppercase. Just stick with that range that you have, okay? That depends on the technology. Some technologies, like I told you, there are 3 formats for the basic quality. There's the Sanger, there's the Illumina, and there's something else, okay? So it's up to the technology if they feel that they have that little precision going from 99.1 into 99.1000 something, then they need more characters to expand the scale, right? So the scale, if you want to increase it from 40 to 70, it depends on the technology. So it's up to you. You want to do that assumption, but made it clear in your answer that you use that scale, okay? If you want to use the scale that we discussed in the lecture, which is the right way to do it, because this is what we discussed, do that. This is the full way of answering, okay? All right? And all of these are excellent questions. Please keep the active way of discussing. This way will be the lectures more, more fun, right? Could discuss many things that I was not planning to discuss in the slides. Okay? Again, anything in the slides, those are the things required from you. Anything we discuss here, really not required, but just for your information, especially the paper that I'm suggesting. So this is up to you, because not all of you I expect to do some research in bioinformatics. All right? Thank you so much. Could end it up here. Have a great day and see you next week. So I can create